Alright, so today we're going to be talking about developments in energy storage. More specifically, we'll be talking about applications in electric vehicles, power grids, and aerospace. I'm Kelvin. I'm here with Zach and Tyler.
Cool. All right, so one of the first things to consider when using batteries is some of their characteristics and how they react with use. So the first one of these is the state of charge curve, and this shows how a battery's voltage changes with how much of its capacitance has been used in its discharge. So you can see from these curves here that the battery's voltage depends on how much of the capacitance. So if this is the total capacitance of the battery, towards the end of its steady charge, you'll have a lower voltage that you have access to than when you first begin the discharge. And this is affected by the rate of discharge along with the operating temperatures that you use the battery in. And then the next measure for batteries is its C rate, and this is a way of normalizing across batteries of different capacitance. So a C rate is a measure of how fast you can discharge a cell, and 1 C will discharge a cell in 1 hour. So if you have a 2 amp hour battery and discharge at 1 C, it would take an hour to discharge and draw 2 amps. But if you have a 3 amp hour capacity and discharge at 1 C, it would take 1 hour still, but discharge at 3 amps. The next characteristics of batteries is their energy density and their form factors. So energy density is a measure of how much energy you have per unit weight or per unit volume for a battery. This can be estimated by taking a battery's nominal voltage and multiplying it with its capacitance, and then dividing by the weight or volume gives you a good estimate. And you can see that batteries vary in their energy densities. And then another characteristic of batteries is form factors. So batteries produced in mass production generally come in certain shapes, and these are cylindrical, button, and prismatic. Cylindrical are very common in the automotive industry, and these are 18650s or 2700s, and this is a measure of their diameter by their height of 18 millimeters by 65 millimeters. Button cells are common in electronics, and so are prismatic cells. The next topic we're going to talk about is battery modeling, and this is a way of characterizing how batteries work during their life cycle. So a battery can't just be modeled as an ideal voltage source because they have transient behaviors that must be taken into account in order to accurately determine what size pack you need or how much energy you need. And a battery's curve can be seen here, and you start off with about 3.8 volts, and then when discharging begins, the battery's voltage drops down to about 3.65 volts, and then you turn off the discharge, and you can see the transient behavior of the battery coming back up to 3.7 volts. A similar thing happens when you're charging the battery, and then its voltage drops back down. And there's 3 basic ways to model a battery. The first is using a zero order model, and this is when you have the voltage of the battery modeled as an ideal source and the internal resistance of a battery, and this gives you your effective voltage. The next is by using a one-time constant model, and this is when you model the first transient behavior. So this is typically like the discharge of the battery, and this involves putting in the capacitor and resistance in parallel, which allows you to model this transient behavior to get a better idea. And then this can also be upgraded to a two-time constant model to get both the discharge and the charge characteristics.
Alright, now we're going to talk about the development of different types of batteries. So first up is lithium-ion batteries. These were designed specifically to be a direct replacement by having a similar voltage per cell to replace nickel cadmium and nickel metal hydride batteries, but also being more energy dense. These batteries currently have the highest energy density of any commercially available batteries. They're very widely used in modern electronics to power cell phones and electric vehicles. The lithium-ion batteries have a positive electrode that can either be made from lithium cobalt oxide or lithium iron phosphate. Changing the positive electrode can alter the battery's characteristics, such as the voltage and discharge rate, and the negative electrode is usually created from carbon, like graphite. The cons of a lithium-ion battery are that it'll catch fire if it's overcharged or short-circuited due to thermal runaway, and it needs to have a specific temperature range for it to work in. So at 40 degrees C, you'd see a 20% performance decrease, and at minus 20 degrees Celsius, you'd see a 50% performance decrease. If they don't catch on fire, the batteries can still build up pressure and puff up.
All right. So speaking of lithium-ion batteries, there's also sodium-ion batteries that is right here. The reason why I did some research on this is we're talking about grid power, which we'll talk about a little bit later in this video. So these were designed pretty much just to replace lithium-ion batteries, but be at a lower cost. A lot of cons is they're actually heavier than lithium-ion batteries, and they actually have a lower capacity. Yeah. They work similar, just as like Kale was saying. A lot of the change in temperature affects it, and just everything. It's really almost identical to lithium ion. That was like the overall goal. Right now, they're not really that useful, but in the future, they may be of something potential. Have some potential. Next, I want to talk about some redox flow batteries. These are actually pretty interesting. I've never actually heard them before, so I had to get a little bit of research on them. How these work is they send like a fluid through here that flows like an analyte and catholyte through the batteries to like convert the chemical energy to electrical energy. And you can see that they actually have to use pumps in these, so it actually takes a little bit of work, a little bit of power to actually produce like what you want. These pros and cons for this is that they actually have long life and they reduce the cost. They also can like take fluctuating energy, which means like like in solar power, if you're constantly like if they take like a huge amount of voltage from like over in the day compared to like night, they can like adapt to that and be okay. Along with like wind energy, where some days are like really windy, some days like the wind's not putting out as much, so they can actually fluctuate from that and doesn't actually harm the batteries at all. Some cons are like high corrosion. They're actually very large. Actually, you can see in this photo that like there's probably like a person right here. You can see how large they are, so it takes up a lot of space, and also that they require energy because of the pumps. All right, and lastly, what I'll be talking about is like liquid batteries. So the cons on these is that they have to operate at very high temperatures, roughly like 400 degrees Celsius to 700 degrees Celsius. Um, they work by like having two liquid metals by another liquid, typically like a molten salt, as you can see in this photo. It allows like current to like flow through easily, which is what I'm mentioning here when I say large current density. It allows a lot more current to flow through a smaller surface area than any other batteries. They're very low cost. They have a long cycle life and some construction. So these also like aimed at the power systems and like how they can be useful for those, which I'll talk about in the next slide. So, like I was talking about the power grid. So, if you don't know what a power grid is, that's just pretty much like a power plant sending out a bunch of electricity through like different houses and factories. And they're wondering how are we going to use batteries to like store the excess energy that the power plant is producing when homeowners don't need it right now. So they have energy storage facilities, which would be looking into like batteries, which I mentioned earlier, which they potentially thought about using sodium-ion batteries just because they're so cheap. But once again, they need a lot more research to be developed. The flow batteries were really nice because the fluctuation, in my opinion, they're probably the best, other than the corrosion and a little bit of work you have to put in. The liquid batteries were the last thing I talked about. Those would be ideal if you were like put them by the power plant where you're having a lot of heat outtake. Then you would use those.
The next topic we're going to go into is the use of batteries in electric vehicles. And the powertrain of an electric vehicle consists of three basic components. It's the battery pack, the inverter, and then the electric motor. And so the battery pack obviously converts chemical energy into electrical energy. And then to use this in vehicles, we have to convert that into mechanical energy for motion. And a very common one used in electric vehicles is a lithium-ion battery. And here you can see a diagram of what the battery pack would look like on the bottom of a vehicle. The electric motor is in the back here, which powers the wheels, and then your inverter is likely in the front. And then this is a demonstration of the inverter. So you have DC electricity coming from the battery pack, and this is passed through the inverter and get three-phase AC current, which is used in an induction motor. And now I'm going to explain how an induction motor works just for clarity. So for an induction motor, you pass three-phase AC current through a arranging of coils, and this gives you a rotating magnetic field. And then you place a rotor in the center of this, and this creates motion, rotational motion in that rotating magnetic field, which allows you to turn the wheel. There's multiple types of motors. Synchronous motors are another AC type of motor, and there's also DC brushed and DC brushless. And then, as I mentioned, three-phase AC current is used to translate motion.
Lithium-ion batteries are used almost exclusively in the aerospace industry for their reliability as well as being the most energy-dense batteries available. The lithium-ion cells can also be built to any size and shape, allowing them to be designed specifically for an application where saving space is essential. Pictured on the right is what one cell might look like. Then multiple cells can be connected, allowing to create a unique form factor for a specialized application. When used in low-temperature applications, a design that retains heat from the batteries will increase performance and efficiency. Batteries used in aerospace will be subjected to extreme forces that are not seen in everyday use. Because of this, many tests are performed to verify that they will not fail in these situations.
These are our references too, if you guys need them. So references here, and these are our picture references. Sweet. Thank you.